just unmute and speak up. Don't hesitate. Then let's get to some spectral attention.
Yeah. So hello, everyone. My name is Dominic, and this is Devin. Together, we will be co-presenting our work on spectral attention networks, which is the full name being Rethinking Graph Transformers with Spectral Attention. And this work was done in collaboration with MILA, which is the Montreal Institute of Learning Algorithm, and Valence Discovery, a drug discovery company based in Montreal as well. And I would like to thank all the co-authors. So Devin here is the first author of the paper, and I'm the co-first author. I would like to thank also Prof. William Hamilton, Vincent Le Tourneau, and Prudencio Tosu for also co-writing the paper and helping us build the ideas. So Devin is doing his master's thesis at Mila, and this is part of his master thesis. So I would like to give him the opportunity to do the presentation, and I will stay mostly in the background to help answer some questions if some questions are tougher than expected. But I think he'll be fine. So Devin, you can start the presentation.
Okay, so thank you guys for that. Thank you, Dom, and thank you, Heinz, for the intro. Very glad to be here. So let's get started. So just some preliminaries. So I'm sure you guys have seen this before, but some of the current GNN strategies we've seen so far are convolutional, attentional, and message passing approaches. In all of these approaches, it's kind of just a sparse message passing approach. And so so what are some of the limitations? Well, there's, we know there's over squashing, there's the WL test that has some limitations in its expressivity. And here there's just a little diagram I have of the bottleneck. So basically you can see there's kind of this over squashing of information that gets lost when we do too much message passing. And this makes it very difficult to model things like long range dependencies. And so we're trying to see in this work if we can kind of move beyond some of these traditional message passing and sparse attention approaches that we've seen so far. Okay. So the transformer, so I'll start with the transformer. Why is the transformer important? Well, it revolutionized NLP by doing exactly what we're trying to do right now. It essentially removed a lot of the inductive biases we see in models like the RNNs and made it easier to kind of model long-range dependencies. And so immediately the question is, can we try and generalize the transformer through the graph domain and see some of the benefits we saw in the NLP space? What's the main challenge here? So the hardest thing is, how do we define the positional encodings for arbitrary graphs? So these are kind of a key component of the transformer here at the bottom right. So at the input embedding, they add these positional encodings just to tell the model what the order, so what the relative positions are of the nodes in the sequence graph for the NLP tasks. And so for arbitrary graphs, really the answer to this lies in the graph Laplacian, and I'm going to explain this in better detail in this presentation. Okay, so previous work. So what are the previous works? So number one, GAT, Graph Attention Network. So this work was very important and first introduced the notion of attention in the graph space. And another work that we're heavily based upon is graph transformers by Vijay Dwivedi and Professor Bresson. So they were the first to introduce a generalization of transformers to graphs. And also for the positional encodings, they used also a Laplace-based approach, but with a simple concatenation and adding of the positional encodings. And this is something, we wanted to touch upon and try to improve in the work, in our work. Okay, so, guys, please stop me if you have any questions along the way. I'm happy to just go right to it. So positional encodings. So the positional encodings used in the original transformer, they're predetermined sine waves, sine and cosine waves on the bottom right we have here. and they're simply just added to the initial inputs. And so another reason they did this is because these positional encodings can be generalized to sequences that are longer than the ones seen in the training set. So that's a big plus. And it's good for encoding just a relative sense of distance between the nodes along the sequence. This process, though, isn't as feasible for arbitrary graphs. The most obvious one is if you look at the equation, right? So the pos variable, it was just the actual position of the node in the sequence. But in an arbitrary graph, there's no real obvious way of defining these positions. Another huge thing is the frequencies. So I'll get into more, but the frequencies are not fixed. They can't be predetermined. In a graph, there's a very specific set of frequencies for each graph. And so it just remains pretty unfeasible. The answer, though, lies in the eigenvectors or so I'll interchange eigenvectors and eigenfunctions, but they're the same thing. So the eigenvectors of the Laplacian. And so for those unfamiliar with the Laplacian, I have two definitions here. So the regular Laplacian is just the degree matrix. So it's a diagonal matrix of degrees minus the adjacency matrix. And then we have the symmetric Laplacian on the right here. Okay, this is symmetric normalized Laplacian. So they still sum to zero, but it's just a symmetric version. Okay. So some basics. So I wanted to give a little bit of basic mathematical intuition behind the eigenvectors that we're talking about. So I'm just going to give a little bit of formalism to explain how it works. So suppose phi is a function over the domain of nodes. So think of phi as a function. It takes in the nodes of a graph and just assigns some real value to each node. Okay. Let ni just be the neighborhood of nodes in i's neighborhood. So the nodes in i's neighborhood. And L an operator on functions over nodes. So operators are just functions that take in functions. So like an obvious one is like gradients, like just the gradient operator is a operator. And so if we look at a very important a vector here, so the vector L phi, what it does is it measures the average difference of a node's assignment and its neighbor's assignments. So if we look at one element of the vector phi, L phi, what we see is that we're taking the size of the neighborhood times the value at phi I, and we're subtracting all the values in this neighborhood. And so intuitively, what you can think of is if the elements in L phi have a small magnitude, then nodes have very similar values to their neighbor's values. Okay, and if we look at the quantity here, so this becomes if we look at the scalar phi transpose L phi, we get this summation of equations here, and it's going to give some value. And the point is, if we can achieve a really small value here on the right, it means, like I said before, that our assignments, the assignments of values to each node, have very similar assignments to the neighborhood. Okay, and really all the eigenvectors they're assignments of these values that minimize the quantity on the right, and that actually becomes the eigenvalue of the associated eigenvector. Okay, and so what's the trivial solution, right? So if we assign each node the same value, then we can see on the top here that each element of the vector will just be zero, right? So we can achieve an eigenvalue here, so a value on the right of zero, by just assigning a constant value to each node. So that's what we call the trivial solution. It also can be used to measure the number of connected components. And then after that, we have eigenvectors that are orthogonal to the previous ones. And the next eigenvector is kind of the assignment of values that minimizes the difference between the values of the nodes. And this can be used to actually define the min cut of the graph. And then we have all these different eigenvectors and frequencies that we have for this specific graph. And if we look at these eigenvectors, they actually look, or they're the equivalent of sine functions and cosine functions traveling through the graph with frequency proportional to the associated eigenvalue. Okay, and so we can actually use these as positional encodings. Here I have a couple diagrams to show you guys. Oh, it's not loading properly. So if we look at kind of the eigenvectors of a grid, if we look at some of the different eigenvalues and eigenvectors, here we can see that on the left here. And on the right, we have different eigenvalues and eigenvectors for a specific molecule. And so we can see for the lower eigenvalues, we have a very smooth changing graph, smooth changing eigenvector. And as the lambda or the frequency increases, we have a quicker moving sine wave traversing through the graph. Okay. So basically a huge component of our work was previous work essentially just took these eigenvectors, so a fixed number of eigenvectors, and added and concatenated them as positional encodings. And here we address some of the key challenges in doing that, and why we think it's and what we think we need to consider when using the eigenvectors for positional encodings.
Yeah, can I first ask a bit about the eigenvectors or the Laplacian itself in general? So we have a graph, and our graph can be represented as the adjacency matrix. And then from the adjacency matrix, we can calculate the Laplacian and the normalized Laplacian. And is there a one-to-one mapping from isomorphic graphs, like from the isomorphism class of a graph to the Laplacian, or are there like multiple Laplacians or multiple graphs with the same Laplacian that aren't isomorphic?
Yeah, so I think Dom will help me a bit on this, but basically two graphs that are non-isomorphic will not share the same Laplace spectrum. So one thing I was going to expand about a little bit is actually we can use the spectrum eigenvalues to differentiate two different graphs. So I'm not sure if that answers directly. Maybe Dom can add a bit what he thinks here.
Yeah, so for your question, you're saying that if they share the same Laplacian or the same Laplacian eigenfunctions. Because for the same Laplacian, it's exactly the same question as asking it for the adjacency matrix. Basically, like two graphs that are isomorphic can have like different adjacency matrix because you can permute the rows and the columns of that matrix. And the same is true for the Laplacian. For the eigenvectors, in general, like if you have a set of eigenvalues and eigenvector, you can retrieve the Laplacian matrix from there. So each set of eigenvalues and eigenvectors map to a single graph. But a single graph can map to different eigenvalues and eigenvectors only in the case where you have multiplicities, so two eigenvalues that are the same. But it's not such a big problem because it's just like when two eigenvalues are identical, you can find linear combinations of eigenvectors that are also acceptable eigenvectors. And it just means that there are two sets of frequencies, two places in the graph that resonate at the same frequency. You can view it like that. And I think Devin will discuss more how we deal with the multiplicities in later slides.
Okay.
So there's a question in do you have a simple example to see that? Can we go back on the image, on the images of the eigenvectors and put the molecules? Well, you can see here in both the molecular graphs, we have lambda equal 1 2 times. And in this case, the eigenvectors are represented here, and they mostly do not intersect. because of the optimization algorithm that generates them. But in theory, you can take the two eigenvectors that you see, and you can take any linear combination of these two eigenvectors, and they will still be valid eigenvectors. But in practice, due to the way the eigenvectors are computed, and they generally do not intersect much.
Okay, but what we show here in these graphs, right? That is, we always have we have our Laplacian matrix now, and we calculate its eigenvectors and its eigenvalues. We always have an eigenvalue like lambda1 and its eigenvector. And then for each value in the eigenvector, we have the associated node, and we color the node according to the value in the eigenvector. So, yeah. Okay.
Yeah, exactly. So here the dark pink represent the negative part and the dark green represent the positive part. And the closer it is to white, the closer it is to 0. For example, here.
Yeah.
So things that you can say about eigenvectors, but Devin will go into more details, but you can flip the sign. So you can flip the green and the pink, or you can take, if the two lambdas, lambda1 and lambda1 are identical, then you can take a linear combination of these two eigenvectors.
I'm just about to get into all of this, so maybe it'll be a bit clearer.
Yeah, sorry. Let's get to the eigenvector etiquettes.
Yeah. So that's what I was about to get to. So I'm gonna just go over these in a little bit slightly more detail now. We can maybe a bit more clear. So one big thing, like I said, here we're looking at some of the key challenges in directly concatenating and adding the eigenvectors as positional encodings. So number one, and this is a pretty obvious one, is basically given an eigenvector phi, c phi, where c is a constant, is also a valid option, and we must pick one vector in kind of the span of phi. Right, so all vectors in that span are valid, and we really need to select one. And so what we should do is typically just select a normalized eigenvector, such that the dot product is 1, or the norm is 1, right? Another big one, so that we think was really important, is incorporating information about the eigenvalues, right? So if we look at the top right here, basically we have on A kind of the trivial way of viewing the eigenvectors in just a simple ordering. And on the right, a more sophisticated way of seeing that the frequencies actually define kind of a distance between the eigenvectors. And we think it's important to kind of include some of this information about the relative position about the eigenvectors. The eigenvalue obviously supplies value information, right? It tells us what the frequency of this eigenvector is. And the eigenvalue, the spectrum, also provides a lot of information about the graph structure. So on the right, we have this example of two graphs that are non-distinguishable by the WL test. But if we just look at the spectrum of the eigenvalues, then we can actually distinguish them, right? And other important physical properties depend on the eigenvalues. On the left here, we have heat diffusion. This is an important property. And the biharmonic difference, the biharmonic distance, sorry. And so it's a way of measuring kind of heat kernels between nodes in a graph, right? So we think that just summarizing how, it's important to include information about the eigenvalues. Number 3, so multiplicity. So this is another big one. So basically 2 eigenvectors can have the same eigenvalue. And not only do we need to try and, pick between which one to use, but actually any vector in the space spanned by both is also valid. Right, so this is even more challenging, right? So how do we deal with these eigenvectors of repeated multiplicity? 4, this is another really big one that we think is really important, is basically, so a graph G can have at most n linear independent eigenvectors, where n is the number of nodes in its graph. And in prior work, often what they did is basically they would select a fixed number k eigenvectors, and for each graph, we would take the first k eigenvectors, first k non-trivial eigenvectors. And one thing that's very important here is if we do this, we need to make sure that k is less or equal to the smallest number of nodes in our data set. Because let's say we want to pick k equals 10, but then we have a very small graph in our data set, say of size 4. Well, we won't be able to take the first 10 eigenvectors because there simply aren't that many eigenvectors. And then we're trying to learn these functions that depend on the first k eigenvectors, but we won't be able to do this for the smaller graphs, right? And so this creates a major bottleneck when we have kind of a big tail in distribution, where the smallest graphs in our data set are much, much smaller than the largest graphs. So that'll force us to pick basically a small k, and that'll make us lose a lot of information about the Laplace spectrum for the largest graphs in the data set. Right, so this kind of motivates the need for making a fixed dimensional positional encoding that captures information about the entire spectrum of all the graphs in our entire data set, not just the smaller ones. Number 5, another big thing and a challenging one is given an eigenvector phi, minus phi is also a valid choice. So basically now we have to pick between a possible 2 to the power of k possible combinations where we're picking k eigenvectors. And so this makes it very challenging to kind of pick the correct ones. And previous work proposed to do data augmentations. This is what the graph transformers did. Basically, they did data augmentation where they randomly flip the sign of the eigenvectors during training.
Okay.
So back to, yeah.
Yeah, I think we have a question about your etiquette number 4.
4. Okay, let's go back.
Alice?
Sorry, yeah. When you choose the smallest k eigenvectors, right, or k eigenvalues for those vectors, but if your eigenvalues are the same, do you combine them? Let's say k equals to 3, for example, but 3 and 4 are both, let's say 4, or your eigenvalue is, let's say 0.3 for both of them. What do you do?
In our proposed model?
In the general sense.
In general, so what was done previously was we would just take, let's say we took the first 3 and all first 3 were the same. We would just take the first 3 and kind of lose information about the fact that they're actually the same, that they have the same eigenvalue. So that was what was done before.
Not like a actual, let's say first eigenvalue is always 0, right? But then 2 and 3 and 4 are the same.
Yeah.
But you only take the first 3, so you take 0 and then 2 other ones. Yeah.
Yeah. That would be random. Yeah.
All right. So you don't combine, let's say, because 2 and 3 and 4 are the same. So you create another vector equivalent representing the 3. You don't do that?
Yeah. So this is what was done before.
Okay.
Yeah, this is what was done before, basically.
Okay,
so we would
thank
just,
you.
Yeah, no worries.
Okay.
So is what was done before that we combine the eigenvectors that have the same eigenvalue, or do we just pick them randomly if we have the...
Pick them randomly. So if let's say the first, okay, it's a bad example, but let's just say the first 4 were the same and we're picking 3, we would randomly pick 3 of the 4.
Okay.
But yeah.
I just want to add that there's no way to combine 3, let's say you have 3 eigenvectors and you have to choose 2. There's no way of selecting 2 such that you keep all the information. Because in the end, it's like having 3 orthogonal vectors. You cannot find 2 vectors that have the same plane as the first 3. You always lose information. So, but we think this is not a major bottleneck, because by taking by taking a k large enough, like you can still have enough positional encoding in your graph such that you don't need you don't need to know these multiplicities in the higher frequencies. But yes, it's definitely,
I agree. Like if it's 3 to 2, but you can always reduce 2 to 1, right? It's just a plane, and new eigenvector will be just the diagonal of the two vectors, right? And that change, but that will change your eigenvalue. So is that why? Yeah, they don't
No,
do.
actually, no. Even if you have two eigenvectors and you want to reduce to one, it's like the diagonal does not represent the full plane. For example, if you can move only left, right, up, and down, but you cannot reduce it to only moving in diagonal, in the diagonal up left. Like
Okay,
you
okay.
need, even if you take the diagonal up left, then you need the diagonal up right also to represent your two vector bases.
Okay, so in graph, you cannot do it like a traditional vector space then.
Well, what I'm trying to say is that for any kind of vectors, if the vectors are orthogonal to each other, and eigenvectors are always orthogonal to each other. So when your eigenvectors are orthogonal, when your vectors are orthogonal, you cannot reduce them to a smaller subset of vectors.
Okay, all right. I have to think about this. But thank you.
Basically, just want to make things clear. For example, I forgot I could draw, but if you have your two axes like that, then you cannot say that you reduce it to a vector that goes in that direction, because then you cannot go into that direction. If you do that, you have to keep the basis orthogonal.
Yeah, you need at least two vectors.
I see. Okay.
You need two vectors to span a 2D space. You can't span a 2D space in one vector. We have another question.
I have a question here. Maybe you're going to mention this later, but have people tried here like sort of padding with zeros or something, like zero vectors, when k, to pick larger k, and for the smaller graphs just pad with zeros or stuff like that?
Yes. So that's what basically we've heard this before. So basically, if we do that, you can't really do that because, let's say you have like if you take a simple neural network, like it's going to expect an input of a certain size, right? You can't have like some graphs that feed you inputs of size 16 and some graphs that input you features of size 8. Like how are you going to train a neural network where the inputs are constantly changing? Because if you just pad with zeros, like
Yeah, of course, it's not a very principled thing.
Yeah, like it's not like, I guess you could just put zeros there, but like it's not very rigorous, But we need a constant sized input, a fixed size input.
Yeah, I mean, I would agree it's not rigorous, but I was just curious, like if someone actually tried this in practice, maybe it does decently, or
like just pad with zeros.
Yeah,
I think
we haven't tried that. No.
Hi, hello.
Vijay, do you have something?
Yeah, I was trying to raise my hand. I couldn't find it. Yeah, it's hi guys. So I just wanted to add the positional thing, right? I mean, we're discussing about this fixed k eigenvector. So I remember it was first in the paper position aware GNNs, the paper from 2019. So they kind of try to learn the position embeddings for each node based on some selection of anchors. So if, for example, they have k anchors, the number of positional embedding that they would learn is that fixed k. And they have this limitation mentioned in the paper itself that because of this reliance on the number of anchors, they could not do, they could not extend its generalization to inductive tasks. So I'm just recalling that to kind of highlight this problem that we have to, if you're trying to do positional encodings, and we have that challenge that there can be some certain of nodes on which it's dependent. For example, if there's a graph with 8 nodes, there can be at max 8 eigenvectors. I mean, the k that max be to that value. Similar was the case in positional aware GNNs, where if they select k number of anchors nodes, it would be at that point only. And the positional embedding that they generate, for example, if it's k, they try to pool all the k values to generate just one positional scalar when they kind of pass the features in the final layer. So I mean, I think we have to select a fixed K, and padding is one solution, but then it would not provide any information. And if we have a data set with several variable sizes of graphs, if there is 100 nodes in a graph, maybe using all the 100 would not provide so much information, and maybe the later eigenvectors would act as a noise.
Yeah.
And yeah. So yeah, I mean, for example, if it's for zinc and we're using K, there's a K. I mean, even of smaller Ks, it provides a very good amount of information about the structure about the graph structure in the eigenvectors. So yeah, some of the opinions here. You can continue, Devin. Thanks.
Yeah, thank you so much. I absolutely agree with that. And we actually, for all our experiments, never actually use the entire spectrum. We have this kind of hyperparameter M where we just compute the first M eigenvectors for each graph, right? So yeah, we definitely agree with that. Okay, so
yeah,
moving
from Vijay's comment, I take away that like most of the information is contained in a few, or most of the important positional encoding is contained in the first few eigenvectors anyways. Okay.
Yeah, correct.
Yes. Yeah.
And will we also see some experiments on that later?
I would like to. So sorry, Devin. Yeah, I would like to add that yes, the low frequency eigenvector have more give more information about the position, but the higher frequency give more precision on the position. For example, you can view the sine waves of positional encoding as the hands of a clock. So you have your clock with the hour here, and you also have the minutes that's longer, and you have the seconds that's also longer. Theoretically, you can only look at the hours to know exactly what's the time. So only by looking at the hours hand, you can know what's the hour, the minutes, and the seconds, if you have enough precision. But it's difficult to determine the minutes and the seconds looking only at the big hand. So this is where the higher frequencies, they allow more precision. So you have the second hand and the minutes hand and the seconds hand that give you this bigger precision, even though time could technically be told only with one hand on the clock. But still, it means that the higher frequencies are less important unless you need the precision. Devin, you can go on.
Yeah, thanks. So now I'm going to just explain a little bit about the model architecture. So from kind of a first glance, an overview, in the first step, we're pre-computing the first M eigenvectors. So as Vijay pointed out, it isn't really necessary to use the entire spectrum. We can really gain a lot of information from just the first few eigenvectors. So we take the first M and also fully connect each graph while noting which edges were added. Okay. In step 2, we're trying to learn positional encodings for each node in each graph across the data set, and while trying to address the etiquettes we previously described. In step 3, we concatenate the learned positional encodings to the input node features and then apply a main transformer. So the LP over nodes. So basically, the idea is to treat the Laplace spectrum as a variable length sequence, where the eigenvalue is the associated position of the eigenvector. And a transformer is naturally suited for this task to kind of learn the positional encoding. So I'm going to go a little more detail. So if we look on the left hand here, if we kind of compare this to like an NLP task, we have the different eigenvectors. So for each node J, we're taking the node J's element in the respective eigenvector. So we have the different eigenvectors with their associated eigenvalue as the kind of word embeddings. And then we have a sequence of up to length M. In this case, if the graph has less than M, now it's actually appropriate to use padding in this case, since there's going to be a pooling layer at the end that can just ignore the padded kind of words in the in the sentence, and we're not losing any information. Okay. So then we apply a linear layer. This just expands the word embeddings from vectors of size 2 to k. So now we have now we have a k by m matrix. Now we apply layers of transformer encoders, and then apply a sum pooling over the m dimension, which reduces it to 1. Okay, so we've kind of played with the dimensions here, and now we're generating a fixed k by 1 node-wise LPE. Right, so now we have a learned positional encoding for the node that used up to the first m eigenvectors of the spectrum in that graph.
And this, right, what we're looking at right here is only for a single node in the graph, right?
Yes.
Like,
yes.
Okay, and we pick out of all of the different eigenvectors, the m eigenvectors you draw in the beginning, we only pick the jth entry that corresponds to this specific node out of all of those eigenvectors.
If you concatenated all the eigenvectors, right? So each column is a different eigenvector. We're just taking the jth row of that matrix.
Yeah, okay. Nice.
Good?
Yeah.
Okay, and that row is basically this column you're seeing in this diagram. Okay, and then we're just telling the model, okay, what is the eigenvalue? What is the frequency of that eigenvector? Okay. And then we're applying this linear layer, transformer encoders, and then pooling and ignoring the padded words, the padded elements in the sequence, and then applying, the pooling, and then we have this node-wise LPE. Okay. And so what this does is this technique addresses etiquettes 1 to 4. So we use L2 normalized eigenvectors. We're pairing the eigenvalues with their eigenvectors. We're treating the number of eigenvectors as a variable. And the model is aware of multiplicity, so it knows which eigenvectors have the same eigenvalue. The major concern that's unaddressed in this model is the sign of the eigenvector being arbitrary. And so we employed similar to what the graph transformer paper did. We just used random sign flipping of eigenvectors during training. We did propose a solution that does resolve this, but it comes at a computational cost, which I'm going to explain a little bit now. So another way we propose of doing it is instead of defining positional encodings for nodes, we thought of defining positional encodings for edges. And this kind of addresses a very important notion that basically given an eigenvector on its own, it doesn't really reveal any information. If you only look at a single node's value in the eigenvector, it doesn't really provide any information at all. What really matters is delta phi, so the difference in values of the eigenvector between nodes, right? So just like potential energy is always measured as a difference, right? What the state of a given mass's potential energy doesn't really matter. It's more what is the difference in potential that matters. And so another way we thought of doing it is instead of just looking at the nodes, we try to define positional encodings as actual edge features, right? And so if we look here now, instead of just using the rows of the eigenvector matrix, basically we're looking at the difference in eigenvector values along the edges. And we're also looking at the difference, which is the absolute difference, and then the multiplication of them. Okay, and this actually generates completely sign invariant. So whether whether phi1 is negative phi1 or not, it actually doesn't really matter because we're taking the absolute difference in the value and we're taking the multiplication, right? So this generates kind of sign invariant values that we don't have to worry about. And then we can apply the same method as before. So we apply the linear layer, the transformer encoders, the pooling. Now we have these edgewise positional encodings, right? So now the nodes don't have positional encodings, the edges do. Downside is it's pretty infeasible due to the computational burden. It adds an extra factor of n if the graph is fully connected. So instead of now basically learning positional encodings for each node, we're trying to learn positional encodings for all the edges, and we're doing a fully connected model, so that makes it very challenging to do. Okay, so this method addresses all the etiquettes, but as I said, as I just mentioned, the computational burden is very, very high. Okay, I have a question.
Yeah.
Sorry, I have a question again here. Have you thought about like maybe passing the eigenvectors through like an even function to just get rid of the signature, or maybe the other ways, like for instance, if you pass it through some arbitrary function and you do something like f of x plus f of minus x, if f again is like some non-degenerate function, then again that should be signature invariant. Have you thought about something like that?
I think this is something Dom and I were thinking about. We didn't really try it out. Yeah,
because I was thinking it might be more computationally efficient, because if that function f is not something horribly complicated, then it's more like applying an element-wise thing.
Yeah, so like one thing I did try to do is so for each eigenvalue, use the negative and positive eigenvector. So basically now we have twice as many, so m becomes 2m now, where you have twice as many words in the sequence. But I saw no benefits in doing that actually. So I just, it just added complexity and didn't really improve the results. So I just left it as it was and just did the random data augmentation. It had the same effect.
Right, but that's not signature invariant, is it? Like, because I think you can have like 3 and minus 3 and minus 3 and 3, right? And that would not be the same if you, or maybe I'm wrong.
Yeah,
if you just concatenate and change sign, that's not is not invariant to the sign, right?
Yeah, no, it's not. No.
And then we also have. Yeah, go ahead.
Yeah, I would like to add that it's difficult to have this kind of functions that act on the eigenvectors because like because of the properties of the eigenvectors, first being all orthogonal, you cannot compute the intersection of two eigenvectors, so always going to give 0. If you take the max of the eigenvectors, because they represent kind of sine waves, then the max, well, it's kind of sine waves, but they're normalized. So the max depend only on the number of nodes. If you take the mean of an eigenvector, it's always going to give you 0. The sum is always going to give you 0. So it's kind of difficult to do statistics on eigenvectors and things like that. So by using the transformer here, what we hope to do is that the function that we use to project the eigenvectors into a fixed space is learned instead of being something that we engineer. Does that make sense?
Yeah, sure. I mean, here's more like a purely engineering-based question. I guess, like, there's no magic function here, but like it would be something that could reduce the computational burden, and maybe it works. And after all, you still process this through some highly nonlinear functions in the end. So, if you do that at pre-processing time and maybe it works, I don't see why not,
Yeah, it's definitely something that we are thinking about. There are other ways than using a transformer for the positional encoding, but for us it seemed like the natural choice to try. But as long as you respect the etiquettes that we've proposed, and as long as you don't do basic statistics that such as mean and max, like if you find a good nonlinear function, you can replace the transformer encoder from that part. But it's not something we have tried to do so far.
Makes sense. Thank you.
Okay, so moving on. And then we apply the main graph transformer with the positional encodings added or concatenated to the input node features. So the framework here is very based on the previous work from the graph transformers paper. We just apply multi-head attention. We're basically, so H is the number of heads. So we're just concatenating the different heads of the transformer with O is just a linear function. So I won't go into too much details here, but this is just very similar to a regular transformer. And the main thing we're trying to do is learn these weights, right? So how do we want to weigh the different messages coming in from all the different nodes in the graph? And two key additions we made here is separate weights for real and added edges, right? So if nodes I and J are connected in the original sparse graph, then it runs this through these parameters here. And if they're not, so they're added edges, and there's a whole different set of parameters we're trying to learn. And then another thing I introduced is basically a hyperparameter that tunes the weight between local and global attention. So if you set gamma, so this hyperparameter here to 0, then it sets all of these weights from the added edges to 0. So it returns a sparse graph. And as we gradually increase gamma on the range of 0 to 1, so setting it to 1 would basically just set an equal amount of weight between real and added edges. Okay. So then here's just another overview of the model. In the early steps, in the pre-computation steps, we're calculating all the eigenvectors of the Laplacian. And we have these sequences of variable length up to m. If the graph has less than m nodes, then we do padding. Then we learned positional encodings based on these eigenvectors, and these are concatenated to the node input features in the node version. And then we basically just apply the transformer that I just described, which uses the node features here, ed features here, and we're trying to learn basically the weights here. Okay. Limitations. So the node LPE is the one we basically use in all the experiments, and it still doesn't directly address the sign invariance issue. Computational complexity is another big thing. So the node LP acts in n cubed. So each transformer takes n squared time, and we have n nodes. And then the edge LPE has an extra factor of n because we're doing there's n squared edges if we're fully connecting the graph. And the main graph transformer isn't as computationally expensive, it's just n squared.
Can you explain a little bit why we're dealing with n cubed in the, like, I would imagine it to be n squared if we just have our number of nodes and the quadratic complexity of the transformer, and we process the positional embeddings or generate the positional embeddings for each node separately.
So like instead of applying a transformer on each graph, we're now applying a transformer on each node. And the length of the sequence, so if we use up to, so it's technically m squared n, because the length of the sequence is up to m, but if we just generalize m to be n, then each transformer takes n squared time, and we're applying it on n nodes, not one graph.
Okay, I couldn't completely follow there. So n is n is the number of nodes. Is that correct? Yeah. So per graph we have a complexity of n squared or a complexity of n cubed.
Let me go back. So do you agree that basically if you apply the transformer on the graph, it would take n squared time?
Yeah.
Okay, but now the thing is, we're not applying it on a graph. We're applying it to each node in the graph. And there's n nodes in the graph. So we're applying n squared n times.
Okay, yeah, well, maybe I'm the only one hanging here, so let me not keep up the whole discussion. But
Yeah, no, okay, but like imagine you just had one graph,
yes,
okay? You apply the transformer, it's gonna take n squared.
yeah,
But we are applying this n squared thing, now we're applying it n times because we have to apply it to each node.
okay.
So it takes an extra factor of n.
Why would we do that? Like, why is that? Mhm.
So if we go back to the LPE, let's just go back. If we go back to the LPE, this is applied on each node, not each graph. Each node of each graph.
And we are saying that the we're letting the number of eigenvectors act as the act as the sequence length.
So if you want to be specific, it's actually m squared n, where this takes time m squared, but that's bounded by n, right? So we can just say up to n squared, right? So it's bounded by n squared. And then we're applying this thing for each graph n times.
Yeah, if we were to use all eigenvectors, then it would be n cubed.
Yeah, exactly.
Okay. Well, yeah, that's a question for later that I have then, but let's go on. But yeah, it makes sense.
So now if I go back, basically now, and the edge LP is even worse. It's actually n to the 4 because we're not applying it on each node. We're applying on each edge. And since we're fully connecting the graphs, there's n squared edges. So it's an even extra factor of n. So it's way too computationally inefficient. And then the main graph transformer, so we're just playing it on the graph, so that's just n squared. Okay. Okay, so for the experiments now, we conducted three main experiments, 2 ablation studies. So in this, we're trying to understand how does tuning the gamma parameter, so that tunes the amount of weight towards full attention, how does it impact results? So we applied it on 4 tasks. Here we have zinc, pattern, cluster, mole, HIV. I didn't give a data set description, but I'm sure most people are familiar. Zinc is a synthetic molecular task where we're trying to, it's a regression task. So we're trying to predict some value for the molecule. Here, pattern and cluster are, they're SVMs. So we're trying to just cluster the graph and assign each node to the right cluster. Mole HIV is from the OGB benchmark. We're trying to predict a property of a 0-1 property of a molecule. And so we measure the performance in rock AUC here. So yeah, AUC. So what we saw basically is on the 2 molecular tasks, there's kind of the sweet spot of gamma in the 10 to the -6 range, where we saw best performances. And as we increase gamma too much, performances decrease. And for the sparse, so setting gamma to 0 is also not as good. For pattern cluster, interestingly, we saw just continuous gains as we increase gamma from 0 to 1. And yeah, so that's pretty much it. We're trying to understand here, is there really any benefit in increasing the amount of long range weights for these tasks? Okay. Then we took we took the sparse models versus the full models, and also measured with and without using the actual node LPs. And across all data sets, we saw best performances in doing full attention with the node LPE and with the gammas tuned from the previous section. The strongest gains were visible on using the node LP was very effective on zinc and mole HIV, and using full attention was very had good performances for pattern and cluster. Okay. And then we compared, then we took the best working models, the full with the LPE, tuned the hyperparameters even further, and compared to state of the arts. And we did very well on at the time. So these results have been beaten already by now by quite a bit. But at the time, we had the best results for zinc pattern and cluster. And we did all right for MolHIV. It's kind of a tricky data set to tune off. So my best test results came at lower validation scores. So at our best validation score, this is what we got. Yeah, so one thing is we did, we outperformed most of the all the attention-based models on our tasks, and came very close to the state of the arts on MolHIV. So yeah, guys, that's pretty much that pretty much concludes the presentation. As a conclusion, so this is the first successful fully connected GNN model to perform well, or relatively well. Outperforms other attention-based models by a wide margin. But one thing to address is there's a huge computational bottleneck, especially with the edge LP. So further work can hopefully address this by, hopefully by applying transformers that scale linearly or logarithmically, or changes the architecture altogether. So yeah, I just want to give you guys a big thank you. Thank you so much for having me. I think Dom wants to add a couple words here, and I'm very glad to continue discussing, go back and discuss things that maybe weren't too clear.
So thank you, Devin, for the presentation. I think it was very good. I would like to invite everyone also to follow us on Twitter and on LinkedIn. So we put our Twitter names here. Mine is Dom Biaini, Devin is Cruiser Devin, and we also have the Valence AI for our company, Valence Discovery, that is specialized in using AI for good. So for those that are interested in health applications, we're one of the best companies out there in that field. We work in theoretical research, for example, graph neural networks, as you have seen here, or self-supervised learning and meta-learning. And for those interested more in the application, in the biological application, we also work on generative design, molecular optimization, molecular search, and this kind of stuff. So don't hesitate to follow us. And if you have questions, I think it's already, well, depending on your time zone, but in my time zone, it's already noon, but I'm still available to answer your questions if you have any.
I have a quick question. Is it possible to incorporate spatial information? Because if you are dealing with a molecular structure, it's not really flat, right? Like, can we expand this into like three-dimensional,
Yes, so this could be done quite easily. So instead of taking the eigenvectors of the graph, you could take the eigenvectors of the 3D point cloud. And this would give you effectively the 3D structure. The problem here, like when dealing with molecules, is that most of the time molecules are dynamics and have different 3D structures. But it's not always the case. For example, we have seen with AlphaFold, protein usually have a stable structure, and they could be defined. You could use, for example, the distance matrix of each amino acid, and use this to compute the eigenvectors of the Laplacian, instead of using instead of using the graph. Does that make sense?
Yeah. Thank you.
Another thing though is so I'm not sure. I feel like for some tasks, the 3D position is often just given as a node feature, right? So we don't really have to learn them.
Right.
Right. You know, like we already like those. Yeah, those like they're already given in as node features. Now we're trying to learn basically a soft inductive bias about the adjacency matrix, right? So that's something sometimes already provided in the data set.
Okay, good to know.
Christian, go ahead.
I have a more general question. about transformers. So I haven't really followed the transformer for graph literature that much, but I noticed there have been like also the Graphormer recently, which I don't know very much about how it works and stuff like that, but I imagine maybe you probably had a look over it. And I was curious, you know, what would be kind of the main qualitative differences from your transformer? I think theirs was kind of doing a bit better on molecular graphs. Like, do you have any insights? What sort of thing in their approach causes that boost in performance? You know, could their approach be improved by what you did here with these eigen functions? So yeah, it's just a very general question.
So yes, Graphormer was released almost at the same time as our work. So when we say we're the first graph transformer to perform well, it's actually 24 hours before Graphormer was released. So we're still the first, even though it's a very close race. One thing I would like to say about Graphormer, about their performance, is that it's very, very difficult to compare the performance of our model to their model because they use pre-training for molecular data sets. So what they did is they used the PCQM data set from OGB containing 4 million molecules, and they pre-trained the prediction of quantum properties. And by doing that, they have a model that is about 10 times larger than any other model that's proposed on MolHIV and MolPCBA. And they transfer the learning to these smaller data sets. So, for example, MolHIV has only 45,000 molecules, but they pre-trained on 4 million. And this gives you an idea of like how they achieved such a good performance. And because in their paper they never report how their model performs when training from scratch on smaller data set, it makes it quite difficult to compare. However, something that's very interesting that they show is that pre-training on quantum physical properties that are simulated in a computer simulation can actually help in some drug discovery projects. So that's a very important conclusion of their work. Regarding the technical aspect of their work, there are some things that are quite similar. The fact that we use a positional encoding for nodes and a positional encoding for edges, this is something they also do in Graphormer, where they separate the two. Where they use both at the same time, but in a different way. So instead of using the eigenvectors of the Laplacian, they use distance metrics. I don't remember exactly which distance they use to measure, but they use the pairwise distance between each nodes. When you look at the learned positional encoding that you see here on the right, in this part, well, it's if you use the one for edges, I don't know, Devin, could you go to the slide for the edge positional encoding? Well, by doing this here, the subtraction of one eigenvector by the other, it gives you a distance along one axis. And by doing this one, it gives you a distance along another axis and another axis again. So in this sense, our work is quite similar to what Graphormer has done, but they have specific ways of measuring distances, whether our method is a more general and theoretically more powerful. Empirically, it's difficult to know which one is more powerful, but theoretically, this work is more powerful than the Graphormer work. Again, I would like to emphasize that because Graphormer was done by Microsoft, they had immense computational resources, and their model is about 10 to 100 times larger than the models we proposed on the same data sets.
Yeah, thanks. Yeah, I think on MolHIV, they have like 47 million or something like that, which is crazy. Well, is that like, did they actually perform pre-training also on the officially reported results, like in, I don't know, like on the All HIV leaderboard and stuff like that? I imagine that shouldn't be allowed. Like, I mean, it's not really fair.
Yeah, it's not about being allowed or not, but I think a simple notice to say that it's pre-trained would be good.
Yeah, I mean, it should have some disclaimer, like some asterisks or something in the table or whatever.
Yeah, exactly.
Well, in the leaderboard table, if you look at the OGB leaderboard, it says Graphormer pre-trained on PCQM4M. So they specify.
Okay, so it does match. Yeah.
And they also say it in their paper that they pre-train on the large data set, but they put the non-pre-trained models in the same table and never show their own performance, like nowhere do they show their performance if they don't pre-train on PCQM4M. But and my main qualitative difference maybe between Graphormer and spectral attention networks would be that spectral attention networks is kind of principled, and the Graphormer, they try to throw a bunch of different metrics into into a neural network, and then they probably found some that work well. Okay, then Johannes, I guess.
Hey, thanks for the great talk. Very interesting stuff. One question which I had is, I think you mentioned that you fully connect the graphs as a pre-processing step.
Yeah.
How do you sample the edges which connect the graphs? And maybe a second question about this is, did you measure the impact of your connection strategy somehow on your results, or was this something you didn't observe further?
So yeah, sorry. So you asked, how do we sample the edges?
Or yes, this might be confusing. What I mean by that is, how do you fully connect the graph?
Yeah, basically, so when we have the initial graph has some existing edges. So we just note those ones as the ones that are true, so real edges. And then we just literally add connections between all nodes that are unconnected and just note those as edges that were added. And then in this, and then at the bottom here, so then we have this kind of indicator variable. And if the edges were truly connected initially, we applied this set of parameters. And if they're not, so they were added, then we just applied this set. And that's it. So we just basically have an indicator variable letting us know which edges were there initially and which ones were added. There's no random sampling. There's no random sampling happening. It's just that's really all it is.
Sorry, I might have misunderstood then. So your eigenvectors are based on the original symmetric normalized Laplacian, not on that of your fully connected graph.
No. If you did that, then there's just basically one the same. I think they're all connected. So the only way you can minimize it is just a constant. So no, you can't do that. Yeah. And then your second question was how do we?
Irrelevant now because I misunderstood. I thought you wanted to avoid a situation where you have several connected components in a graph, and you edit the graph such that all graphs are connected. But since there's no randomness in the way in which you produce this fully connected graph, there's no impact to study. Thanks a lot for the clarification.
No problem.
Okay, then I wanted to ask, like for mole HRV, for example, what is your M? How many eigenvectors are you using?
I would need to double, it's been a while since I ran it. I think it's about 10 or between 10 and 20. I always use 10 and 20 for all experiments.
Okay, yeah, I just wanted to know, like 3 or like 50?
No, yeah, I think between 10 and 20.
Okay.
We've done a few experiments lower than 10, and the result decreased in performance, showing that like not only low frequencies are important, but also high frequencies.
Yeah. Vijay, can you maybe say how what you used in your paper?
Yeah, hi. So in our paper, we don't we tried doing on mole HIV, but I think the results were not so good. And for zinc, it was 8 eigenvectors.
Okay.
And we also actually for mole HIV, there were some graphs which are very small, like 1, 2, 3 nodes. So we also tried to filter out, because there were only few graphs such graphs which are very actually small, like even less than 2 or 3 nodes.
Yeah, that's that's actually how I started realizing it's important to use a fixed size. Because when I tried applying their model on mole HIV, it's when I realized that so for the smaller graph, if we had a node, like a graph of 3 nodes, then we can only use k equals 3. That's how I actually had made that initial realization.
And yes, one small thing I wanted to add to what Dominic said earlier about like how high frequencies eigenvectors may be useful. So I agree with, like, if they are combined with the eigenvalues, like how you do in this spectral attention, it's really a good idea. And then how the later eigenvectors can also be very useful, like you show with the mole HIV.
Okay. Then any other questions? Otherwise, yeah, can we maybe go back to the to your first architecture slide, like where you show how we get the positional encoding for a node, the node wise? Yeah, exactly.
This one.
Yeah, like have you, like, why are we doing the transformer with the sequence length m instead of having this, yeah, this just be a vector that we have as one single token, and then we have the transformer going over the node dimension, so over the number of nodes.
So yeah, so I think Dom can also analyze, but the main inspiration for this came from this diagram on the top right. So this is mostly actually Dom. So maybe Dom, if Dom wants to talk about it, I don't mind. But like the main idea is basically like looking at eigenvectors as a variable length sequence with a very specific position that's given by the eigenvalues. We actually even tried doing things like encoding the eigenvalue, like the original transformer paper did, where we have a vector of different sine waves and the position value. So like, yeah, so we actually tried encoding the like the transformer paper did here, where the position value is the actual eigenvalue. So that's one thing we tried, but didn't see too much success with doing. But like I said, it's mainly from this intuition that we're trying to envision these eigenvectors as sequences, as a sequence where the position is variable, is not a fixed distance between the eigenvectors. It's really given by this eigenvalue.
Okay, so when we're saying that m equals 10 and we're using 10 eigenvectors, what we really mean is we use at most 10 eigenvectors in this sequence, like the sequence length m is at most 10. But if we have a smaller graph that only has 4 nodes, then we can also deal with it, because we have a transformer here that can also deal with a smaller graph where we only have, say, 4 eigenvectors.
It's exactly like the original transformer. Imagine we have sentences in our data set, and we just give a very small sentence. It still works, right? You just pad to the longest sentence in the data set. So that's all we're doing now. If we have a small graph, just pad, and then for the sum pooling, we just ignore the padded elements.
Yeah, this just solves the problem of having,
variable number.
Of not having to add padding. Like, that's what I would say. Like, if we
yeah. We're not losing any information. Let's just keep it like that. We have all the information up to the first m eigenvectors for the whole data set. Whereas what we did before, we could be losing information. And if we, let me just add that if we wanted to use the entire Laplace spectrum of the entire data set, we can easily just let m be the largest number of nodes we have in the data set. And then we have the entire spectrum of all graphs. But as we've already talked about, it's not the later frequencies aren't as important. And so for computational purpose, we just added this first m parameter.
Yeah, okay, that makes sense. But I was just thinking, is there a way to also have interaction between the positional encodings of the different nodes? Like, say we go up to, we generate our positional encoding up to some number of features km, and then when we arrived at km, we don't do sum pooling, but we have a specific number of Curie vectors that pay attention to our m different tokens, and then we end up with a specific number of tokens, like let's say C, and then we do attention over the nodes before concatenating it to the main features and having the main transformer.
Yeah, this exact train of thought is exactly what led us to thinking about the second proposal here, so over edges, where you bring up a very good point. Basically, in this case, we're applying the LPE, we're applying a transformer on a single node, where it's not kind of learning, it doesn't have information about what the other nodes' values are. So that's exactly why we started proposing this second version over the edges, where it has it knows exactly what the eigenvectors, the values of the nodes' eigenvectors has in its neighborhood. And so this is a lot more theoretically sound, and it's also sign invariant. So one big issue here is we're doing attention between the elements in the sequence, where the actual sign difference between them doesn't actually mean anything. It has no, it's kind of hard to explain, but basically, like, the sign of phi1 is completely independent of the sign of phi2. And then we're doing this attention, and the information is kind of not very important. Whereas here, the sign of this of these ones here, it represents more accurate. Anyways, yeah, I'm kind of losing my train of thought. But anyways, what you're trying to say is kind of why we tried to propose this LP over edges.
Yeah, okay, but I mean, instead of the transformer, we could, for example, also use a deep set model on the on the m eigenvectors, or sometimes, well, we have less than m, and that's why we need something that can handle a different number of inputs. Okay.
No, you don't have to use the transformer. You're definitely right about that. We just elected to do it.